And go ahead. Thank you.
So thank you very much for the invitation, for this very, very nice presentation. Yeah, so the topic is dark and shiny dresses around black holes. I will try to talk about how we can possibly detect different types of black holes and what is the interplay between black holes and the environments they're in. So in particular, we'll talk about baryon accretion onto black holes as a possibility to detect them. This is the so-called shiny dress, which the one that I am calling shiny dress. And then the interplay with the dark matter, so the possibility in particular to detect like dark spikes, so spikes of dark matter around black holes, and possibly shed light on the nature of the dark matter with this method. So yeah, here's my outline. So I will sorry, yeah, okay. So I will talk. I will give an introduction about different types of black holes that we know, and what is the nice interplay between the study of black holes and the study of dark matter. And then I will talk about baryonic accretion onto black holes, and how this phenomenon can allow us to reveal the presence of black holes possibly in our galaxy. And I will focus on both astrophysical and primordial black holes. So hypothetical primordial black holes will be a big part of this talk. And then finally, we'll talk about the interplay between black holes and dark matter, and the possibility to detect spikes of dark matter around black holes in the universe. So yeah, some introduction about the black holes that I will talk about. So the black holes that we know we know the existence of astrophysical black holes, so stellar mass black holes that are a bit more massive than the sun typically, and they can be revealed, for example, when they accrete matter from a companion star. And these nice objects that you can see in the X-ray are called X-ray binaries, and those were basically the first indirect detections of black holes in the electromagnetic spectrum. Then we know massive black holes, actually supermassive black holes that are sitting at the center of galaxies. Those are way heavier than the sun, like millions of billion times heavier than, more massive than the sun. And they are observed up to very large redshift, so at cosmological distances. And their existence is very challenging to explain, because we don't really know how they formed and how they could accrete so efficiently to become that massive. And then we know about again stellar mass black holes that are a bit heavier than the ones that are revealed as X-ray binaries, but still should belong to the same category. So it should be basically the end point of stellar evolution, and their mass ranging around like 10, 20, 30 times the mass of the sun. And these black holes are the ones that have been detected with LIGO and Virgo. So this new and very recent breakthrough in science, the detection of gravitational wave events coming from the merger of stellar mass black holes. So this is another population of black holes that we are measuring up to cosmological distances. And you see, these are typically in the same ballpark in terms of mass as the ones that belong to X-ray binaries. So the blue dots compared to the purple dots in these plots, but a bit heavier. I mean, like getting to 40, possibly even more solar masses. So, I mean, this was not well, maybe not unexpected, but still not obvious at all. I mean, the existence of black holes that mass with a mass as large as 40 times the mass of the sun was not obvious at all before this discovery. And so, okay, there is a debate actually in the community whether the origin of these black holes is astrophysical or maybe a different one, as I will see in a moment. So in general, there is a debate in the literature about the existence of another category of black holes that are more exotic. So they are called primordial black holes. Primordial because they should have formed in the very early universe before BBN, before the Big Bang nucleosynthesis. And this idea is actually not new. It was proposed by Hawking for the first time in 1971, this famous paper. And they could have formed in the very early universe, deep in the radiation-dominated era, in the very early universe, out of collapse of density fluctuations in the early universe, possibly originated during inflation. So basically, the idea is that you may have, depending on your inflation model, some overdensity in the power spectrum at some small scales, some scales that are much smaller than the scales associated to the structure formation. And when this associated scale re-enters the horizon, if the density contrast is large enough, they can actually collapse and form a black hole. So the early universe is, in the early universe, you have the possibility to form black holes with this mechanism. And this is a little bit of a scheme of what you expect to happen, right? So you form some overdensity at some scale. This overdensity exits the horizon, then re-enters the horizon at some point during in the early universe, in the radiation domination era, and eventually collapses and form a black hole. And you can form primordial black holes in a wide spectrum of masses, actually. And actually, there is a correspondence between the time of formation and the mass scale of the black hole. And there is a nice way to see this correspondence by equating like the gene scale, which is the length scale associated to gravitational collapse, to the Schwarzschild length scale, which is the scale associated to the length of the black hole horizon. And you can see that you can, depending on the formation time, up to around 1 second after the Big Bang, you can have a wide range of masses, all the way up to 10 to the 4, 10 to the 5 solar masses, but starting from very low masses. So in principle, you can form primordial black holes in the early universe in a very wide range of masses. And actually, yeah, the interesting connection with dark matter is that, I mean, in principle, since these objects are stable over cosmological scales, if they are massive enough, if they are more massive actually than like 10 to the 16 grams or so, which is 10 to the minus 17 solar masses. Because, I mean, if they are less massive than that, they are expected to evaporate to emission of Hawking radiation. But if they're more massive than that, they are cosmological over cosmological, they are stable over cosmological time scales, and they could actually be a part of the dark matter in the universe, possibly all the dark matter of the universe, as noticed already by Hawking in the early 70s. Or, of course, they can amount to some fraction of the dark matter in the universe. And yeah, so this is just to introduce the concept of primordial black holes. And then, yeah, another category of black holes that I am interested in is another hypothetical category of black holes, which have not been discovered yet, but I mean, there are hints about their presence, and they're called intermediate mass black holes. So they should like bridge the gap between the solar mass black holes that I discussed before and the supermassive black holes that are in the center of the galaxy. And the mass here should lie in this range, right? Like between 100 and like 10 to the 5, 10 to the 6 solar masses. And this could actually have formed in the very early universe, and there could be the seeds, for example, that gave origin to the supermassive black holes via hierarchical mergers, for example, or accretion. And yeah, so what is the status of the phenomenology on these objects? So in particular, in the field of primordial black holes, we typically look at plots like this. So we look at upper limits on the abundance of these objects as a fraction of the dark matter density. So we typically parameterize their abundance in terms of a fraction of the total dark matter density in the universe. And in different masses, you have very different bounds, upper limit on their abundance. And in particular, in this range, on the right part of the plot, the red part, there have been a huge debate in the literature recently, because there was a discussion whether 10, 20 solar mass black holes could be all the dark matter. And immediately we tried to come up with ways to constrain their abundance and to put upper limits on this idea. So this is the debate that is still going on in the literature, actually. Okay, I will also focus a little bit on this part. So you see, for the very light black holes, there is a window which is still open. So in principle, there are no upper limits here. So I will not cover this in detail, but just to let you know that at very small masses, there is a window that is still open. And in principle, all the primordial black holes in this mass window could be all the dark matter. And this can be probed, actually, because in this mass range, the black holes are expected to emit a significant flux of X-rays and gamma rays that could be potentially detectable, and this emission would be due to Hawking radiation. So in principle, in the future, this window can be explored with future X-ray and gamma ray emission. Well, let me go a little bit over this constraint a little bit more. So for example, in this mass range, in the planet mass range, around 10 to the 28 grams, there are some upper limits from basically from experiments looking for microlensing events, but also some hints. So this is quite nice, right? So there are some hints from this experiment called OGLE, and this experiment is basically monitoring a lot of stars near the galactic bulge and is looking for microlensing events. So events in which the black hole is expected to cross the line of sight and has an impact, a temporary increase in the brightness of the background star. And this hint, if confirmed, could reveal that actually at least a portion of dark matter is embedded in primordial black holes in this mass range. So this is quite interesting. It has to be confirmed from, of course, independent measurements in other regions. And then in this stellar mass range from 10 to 30, 50 solar massive, that's where the shiny dress enters the game, because we recently developed an upper limit and studied an upper limit on the abundance of black holes in this mass range by using this argument. So so the argument is, okay, if black holes in this mass range are a big part of the dark matter, I mean, we expect many of them in the Milky Way. We expect like 10 to the 11 or more objects if they are all the dark matter, or I mean, the corresponding fraction if they are a subdominant component. So the radiation emitted by these black holes when they accrete gas could be potentially detectable in the radio and X-ray band, because I mean there is a lot of gas in the galaxy. They would expect to accrete. You would expect them to accrete gas in the galaxy and to emit a lot of radio and X-ray emission. So that's something I will cover in a while, and that's what I call the shiny dress. And then some other limits on the abundance of black holes in this window actually comes from another observable. So actually from the merger rate of black holes, and and this involves, of course, the computation of the interplay with the dark matter. This is something I will not cover in detail, so I will just flash this. That I mean, you can put an upper limit on the abundance of these black holes by looking at the merger rate. So yeah, let me talk a little bit about this shiny dress. So after this long introduction, so the idea is, okay, that you can detect black holes, possibly primordial black holes, by looking at the accretion of baryonic matter, of gas, of interstellar gas, onto these objects. And this is a very efficient process. It is one of the most efficient processes, actually probably the most efficient processes that we know in nature to transform really energy, gravitational energy and rest mass into heat and radiation. The efficiency is very large, larger than the efficiency of nuclear reactions, and the radiation emitted is in several bands like X-ray and radio is very strong and detectable. So you have to, in order to study this problem, you have to model the accretion of baryons of interstellar gas onto the black holes. So you have to study this problem. And there are many ways to study this problem. So typically, the first step in the literature is to consider this simple approach based mainly on fluid mechanics. So you can compute the accretion rate of matter onto these compact objects by applying the simple fluid mechanics equation, so basically the continuity equation, the Euler equation. And you end up with this very famous formula. It's a textbook formula, I would say, from Bondi, Hoyle, and Littleton, which links the accretion rate, so the rate of matter accreted into the black hole, to the density of the ambient medium, to the mass of the black hole itself, and to the speed of the black hole, and also to the sound speed of the medium. So this is the famous Bondi-Hoyle-Littleton formula that is typically used in this kind of studies. But actually, you can do better than this. So what we did is actually study this problem in a bit more complex way, and we use the up-to-date numerical simulations, and that take into account more physics, more effects, and take into account in particular the fact that when matter is being accreted onto a black hole, there is this phenomenon of radiative feedback. So matter is heated up when accreted onto the black hole, and emits radiation in turn, which ionizes the surrounding medium. So basically, you develop this radiative feedback. You develop an ionization front, which propagates in the surrounding medium. And the property. So you can study the property of this ionization front, and actually you have different types of ionization front with different jump conditions from the upstream and downstream part of the shock, depending on the black hole velocity. So taking into account this phenomenology, you actually have a more complicated picture of accretion of matter onto black holes, and you can end up with plots like this one, which is the state of the art basically in the literature. So you have an accretion rate for black holes that actually increases with speed up to some reference velocity and then starts decreasing. So you have a more complex phenomenology with respect to the simple textbook approach by Bondi, Euler, and Littleton, which implied a basically declining accretion rate with velocity. And actually, you can see from the simulations a rich phenomenology. You can see on the right, you see the black hole is moving towards, in some medium, it's crossing some gas. You form a bow shock in front, and then you have this structure, this ionization front, which has a cometary shaped region. And inside, you have an underdense region where, and hotter ionized underdense region where gas is effectively being accreted onto the black hole. So this is really the state of the art of what we know about accretion physics from the most recent numerical simulations. And yeah, you see here some more details and some formulae. Actually, you see the two regimes. The two regimes correspond actually to, as I mentioned before, the two different types of ionization front that you can have. The D-type ionization front for low velocities, and the R-type ionization front for high velocities. So in particular, the nice feature is that for low velocities, you have an accretion rate that increases with speed. So in principle, you can have, and this is very nice because you can have a very significant accretion rate at relevant velocities, which is something that could have, and as we will see in a moment, has phenomenological implications, because you can really see a very efficient accretion for large black hole speeds. Yeah, so the idea was basically to look at the data and to check if the astronomical data can constrain primordial black holes abundance given all this physics and given all this phenomenology. So we looked actually into mainly two different types of data. So we looked on the one hand on radio data, so in particular the VLA survey of compact radio sources near the galactic center. And then we looked at X-ray data in this, actually in particular in this hard X-ray band at some tens of keV. So in both cases, we had a catalog of sources. Not all of them were identified, but some of them were. And the region of interest was typically near the galactic center, so typically 1 square degree or so near the galactic center. The idea was to understand whether a population of primordial black holes that could amount to all the dark matter in the galaxy and therefore in the universe in general could overshoot by a large amount this number of sources, so that we could place an upper limit on the abundance of these objects. And so in order to do this, so we performed the Monte Carlo simulations of the emission from black holes in the inner galaxy. So we performed the simulation in which we populated the inner part of the galaxy with primordial black holes, assuming that they have some fraction of the dark matter. They amount to some fraction of the dark matter. We took into account all our information from astrophysics, from the distribution of gas in the galaxy, and we came up with simulated maps of the expected radio and X-ray sources. So by comparing the expected number of sources that you would possibly associate to this population of black holes to the actually observed black holes, we could set conservative upper limits on the fraction of dark matter in black holes. And this is the result. This is the result that we got. So we could conclude, actually we wrote 2 papers on this. So the first is based on the Bondi formalism, the simple textbook approach that I discussed before. And the second one is based instead of this more up-to-date and more sophisticated formalism for the accretion of black holes, of matter, of baryonic matter onto the black holes. And in particular, in the second case, we got a very significant, very strong upper limit on the abundance of primordial black holes. So, I mean, we concluded that in this mass range, I mean, the primordial black holes could amount to a fraction, possibly only a small fraction of the dark matter in the universe, like 1 per mil or less. So this is quite relevant result, given that there was a debate in the literature about this. And it is still very interesting because it is actually window of discovery. So, I mean, it is possible that black holes actually contribute to a small fraction of the dark matter. It is possible that possibly they are part of an extended mass function, and there are some peaks of this extended mass function in this mass range. So the fact that we are so sensitive means that this is a potential window of discovery for primordial black holes as a subdominant part of the dark matter. And I want to emphasize that, I mean, the discovery of primordial blacks would be extremely important regardless of which fraction of the dark matter they make up, because this would have impressive consequences on the fundamental physics and the physics of inflation, and actually many consequences that I can discuss more in the last part of the talk. But this is the current result that we have. And actually, okay, just to flash another application. So, I mean, we focused on the primordial black holes, but this method of looking at the radiation that is possibly emitted by matter that is being accreted onto black holes is actually possibly applied to the guaranteed population of astrophysical black holes that we have in the galaxy. And this is very interesting because, I mean, in the galaxy, you expect to have a population of order 10 to the 8 astrophysical black holes, as that should be like the stellar graveyard of our galaxy. And only a small portion of them is visible when they are visible only if they are part of this system called X-ray binary. So the majority of them, the vast majority of them, are absolutely, I mean, they evade, they are unobservable at the moment. They evade all searches in all wavelength. And I mean, what we are studying now here in Madrid with a PhD student is whether, I mean, future experiments, in particular in the radio, will allow to, make this huge iceberg of isolated astrophysical black holes that we expect to have in the galaxy like emerge. And this is work in progress. So we'll just flash some results. So according to our simulation, actually there is a very strong science case for future observatories like SKA, for example. SKA will be possibly, I mean, the big thing in radio astronomy in the next decade, and we will improve the sensitivity with respect to VLA by 1 order of magnitude. And according to our simulations, it will be able to detect a large number of isolated black holes, so isolated astrophysical black holes. So that was my take for the shine dress. And yeah, in the last part, I will talk instead of another possibility, of another nice possibility. So the possibility to detect actually, so here now I will consider a scenario partially motivated by what I said before, in which, I mean, the majority of the dark matter is not made of black holes. So it's made basically of some particles, whatever is your preferred candidate. And actually, the key point of the discussion will be the fact that black holes that formed in the very early universe, and so both primordial black holes and also these hypothetical intermediate mass black holes that have been proposed several times in the literature, are expected to create to form overdensities of dark matter around them and to modify the distribution of dark matter around them. So there is this interplay between black holes and dark matter. Okay, by numerical simulations and also by analytical computations, there were some predictions of what the shape of this overdensity could look like. And typically you end up with power low density profiles around these objects, characterized by some slope gamma. These values, the values of this overdensity are quite relevant. So dark matter is pressureless, so it offers no resistance to being accreted. It behaves very differently from baryonic matter. So in order to compute how this dress is formed, you just have to balance the gravitational pull of the black holes and in the very universe, the expansion of the universe, the Hubble flow. And that's it. I mean, there's no pressure in the game. So given these characteristics of dark matter, you can end up with a very, very condensed and concentrated spike of dark matter around black holes, which can reach very high densities, like 24, 26 orders of magnitude above the average density of dark matter in the universe. So if massive black holes exist, in particular, if you believe that this intermediate mass black holes exist and in the universe, possibly in the center of globular clusters, for example, or in other locations, they could be dressed with this spike, with this very, very large overdensity of dark matter. So the question is whether this can impact some observable and whether this can be detected somehow. And so the last part of the talk will be dedicated to answer this question, and in particular we'd focus on the effect on gravitational waves. So the effect of this dark matter spike on the gravitational waveform. So the context is this LISA experiment, a future space interferometer, which is expected to see more massive mergers compared to the ones that are now observed with LIGO and Virgo. So LISA will be sensitive to lower frequencies and to more massive and larger systems compared to the other gravitational wave observatories. Okay, compared to LIGO and Virgo, to the ones that we have now. And in particular, one of the events that LISA will look for is this category events called extreme mass ratio in spirals. So basically, you have an intermediate mass black hole in the center, so a massive black hole in the center with a mass as large as 10 to the 3, 10 to the 4 solar massive, and a small compact object like a neutron star or a small black hole, small astrophysical black hole, orbiting around this intermediate mass black hole. This system is very interesting because this system would emit gravitational waves, and LISA will be able to detect, will be sensitive to these waveforms. So if the massive are the ones that I discussed, like 10 to the 3, 10 to the 4 solar massive in the center of black hole and the light object around, you expect a frequency that fall nicely in the range that LISA can observe. And the thing is that if you have this dark matter, dark dress around the central black hole, around the intermediate mass black hole, you expect to have an impact on the binary system, and you expect to have an impact ultimately on the waveform. So this is what I would like to tell you about. So what are the ingredients here of this system? So what are the forces that are at work? So of course you have gravitational pull that governs the, you have the obvious gravitational attraction between the two objects, but if you have the back reaction from gravitational wave radiation, so since you're emitting gravitational wave radiation, you have a back reaction in the system. And if dark matter is there, if there is this very strong, very relevant overdensity of dark matter, you expect to have this phenomenon called dynamical friction. So you expect the small object to interact many times with the particles that make up the dark matter halo. And typically, these many two-body gravitational interactions give rise to this so-called gravitational friction. So the small object, the small compact object loses energy, and the energy is transferred via, with a lot of slingshots and two-body gravitational interactions, is ultimately transferred to the halo of dark matter. So you have this phenomenon of gravitational friction. And this, it was discussed in the literature a little bit, that this effect can produce a dephasing of the gravitational wave. So by looking at this system, and you can detect a different waveform if the system is in vacuum or if the system is embedded in this dark matter mini halo or mini spike or dress. And you can do physics with this, because I mean, this effect would be sensitive to the dark matter slope. So it would be actually only visible if the slope is particularly steep. So if the power law is particularly steep, steeper possibly than 2, and in terms of slope. And for example, a detection of this effect would rule out some dark matter candidates which actually are not compatible with such a steep slope. So, for example, if dark matter is made of self-annihilating WIMPs, so WIMPs with a significant self-annihilation, or, for example, ultralight bosons, or if it is a fermionic particle. In all these cases, you would expect some plateau in the center instead of a spike. For example, I mean, in the case of particles with a very large rate of self-annihilation, I mean, the self-annihilation themselves would limit the growth of the spike and would form a plateau. And in general, I mean, for many different candidates, you expect to not to have a very steep spike. So the detection of this waveform, of this effect on the waveform, is actually possible only for very steep spikes. And this allows, and would be very different, as we will see, depending on the slope. So this would allow to, in principle, disentangle different candidates, which would correspond to different slopes and different forms of this dark matter halo. Yeah, so this is just the setup that we studied. So we studied this problem. We wanted to analyze this problem, and we wrote down the forces that are at work. So the gravitational pull, the dynamical friction. So the effect, the force that describes the transfer of energy from the compact object to the dark matter halo, and the radiation reaction written in this way. Actually, so we wrote some energy balance equation. So we basically did the integrated version of the equation of motion, which is easier to compute, and is actually very useful to give some orders of magnitude about the impact of these forces. So actually, a very useful thing to do when you write this energy balance is compare the. So basically, what do you have? You have the orbital energy of the system. The orbital energy decreases because you have emission of energy loss due to gravitational emission, and you have energy that is transferred to the dark matter halo due to dynamical friction. So you have these two loss terms, and eventually you lose orbital energy. And what is useful to compute and to discuss is whether the energy that is lost by the system and transferred to the dark matter halo due to dynamical friction is comparable or not to the binding energy of the halo. So that's a question which was not addressed in the literature. So we would like to understand whether you are, with this dynamical friction, you are actually transferring really a lot of energy into the dark matter halo, and you basically can unbind the halo itself. So you can destroy or partially destroy the system. So that's the first thing that we did, and we actually found a very interesting thing. So we found that the energy lost by dynamical friction when spiraling from some initial radius R1 to some final radius R2 is actually much larger than the binding energy, the gravitational binding energy associated to a shell comprised between R1 and R2, or no, I think Ri and Rf in this notation. So this is very interesting. So you cannot study this system without taking into account the feedback on the halo, the fact that the halo is heated up by this phenomenon of dynamical friction, and eventually its properties is expected to change because of this. So we realized that really the feedback on the halo was important, because the energy pumped into the dark matter halo, into the system, was order of 100 times larger than the binding energy of a shell in this particular configuration. So yeah, this was interesting. So this motivated us to study the system in with feedback. So it was something that was not done before in the literature. So we modeled the impact of dynamical friction on the phase space distribution of dark matter, and we came up with a semi-analytical prescription for this phenomenon, backed up by n-body numerical simulations. And the formalism is conceptually quite simple. So we basically think in terms of a distribution function for our dark matter halo. The integral of this distribution function in phase space is the number. The integral in the velocity space is the number density of particles. And actually, you can write this kind of equation that you see on the left, in which basically you change the number of particles associated to some energy, so in some region of the phase space, because some particles are upscattered by dynamical friction, and the probability of this upscatter is characterized by this p epsilon, and some other particles are from lower energies are upscattered to the current energy. So basically, you're moving particles in your phase space because you are injecting energy into the system. So some particles are upscattered and they are removed from your portion of phase space, and some others enter your portion of phase space because they are upscattered from lower energies. And okay, so here are some more technical details that I can skip, because actually I would like to show you this movie, which is probably more illustrative. And here you see the evolution of the profile of the spike, of the dark matter spike, during the inspiral. And you can see that while the inspiral progresses, the dynamical friction is pumping energy into the spike and is moving particles to larger energies, so to basically less bound and outer orbits, and is therefore altering the profile of the spike. So this is basically what happens. In particular, in the first part of the spiral, if you noticed, this effect was more relevant. You see this alteration of the profile of the spike is more relevant in the first part of the spiral when you're farther away from the center. And then the reason is that when the inspiral progresses, you are more and more dominated by gravitational radiation losses. And so dynamical friction plays a minor role in the last part of the inspiral. And so okay, with this formalism, we get this result. This is our main result. So basically, you can produce plots like this, in which you have the frequency of the waveform. This is called a spectrogram. So you have the frequency of the waveform as the function of time, and you have the vacuum case as the reference case, so the case in which you have no dark matter at all. In blue, you can see how the merger would look like if you had a static dark matter spike, a static distribution of dark matter as the one that was previously considered. And if you consider this feedback on the spike itself, you have the red lines that correspond to a dynamic spike when the feedback is taken into account, and for different slopes of the halo. And you see that okay, you have a big impact, you still have a big impact because you have an anticipated merger, but way less strong than previously computed. So the impact of the spark is very, very relevant. But the cool thing is that it's still observable. So you still expect to have an anticipated merger by few days or possibly weeks, depending on the slope of the spike, with respect to the case of vacuum. So you would, with LISA, you can really see, you can really detect a different type of waveform if you have this effect. So if the dark matter is present around the black hole, you expect to see an anticipated merger because of the effect of dynamical friction. Yeah, this is the same result, but for different mass ratio. So it's very similar. And yeah, this is the same result, but visualized in terms of dephasing. So instead of plotting a spectrogram, so the frequency of the wave as function of time, I plot the difference between the number of cycles that you expect with respect to the vacuum case. So this is another way to visualize the same result. So you expect to have a different number of cycles over a given time, starting from some frequency to the final frequency, if you have this effect or not. And this is why we call it a dephasing of the waveform. And this is very relevant because it's actually, there is an interesting circular argument here because in order to detect this, in order to detect this signal, you have to model it properly. So, I mean, given these matching filtering techniques that are used will be used in the LISA collaboration to detect this signal, you need a template bank. So you need a database of all possible waveforms that you expect to detect. And so if your template bank does not include this effect, you have the possibility to miss this relevant signal because the physics associated to this effect is actually not involved, not encoded in the signal itself. So so this is one of the reasons why it is very important to study this problem, and I consider it a very promising avenue. I mean, towards really detecting the dark matter in this peculiar way around intermediate mass black holes. So yeah, I think it's time to wrap up. So these are my conclusions. So I try to convince you that there are very nice. There are several ways to detect black holes, and there are very nice interplays between the physics of black holes and the dark matter physics. So you can detect both astrophysical and possibly primordial black holes by looking at the radiation accreted by baryonic matter onto them, and by looking at this multi-wavelength radiation, it is possible to determine an upper limit bound on the abundance of primordial black holes in the galaxy and in general in the universe. On the other hand, I showed that the accretion of dark matter instead of baryonic matter can have an observable effect on the waveform in a peculiar system, which is called an intermediate mass ratio spiral. And this effect is potentially detectable with a future interferometer, with the future space interferometer like LISA, and can open up the possibility to detect overdensities of dark matter around black holes. So yeah, this was all.
Thank you very much. Sorry, I'm turning the video on. Meantime, I just. So thank you very much. It was a very nice talk. Yeah, are there any questions? So while waiting for people to chime in with questions, so you are mentioning LISA. LISA is planning 2035, 2034.
Yep.
Is it, so we should wait 15 years, or like, are there any synergy like with, so can Euclid or the frequency are completely different? Can we have some input for?
I think okay. So while we wait for 15 years, we can we can do a lot also with LIGO and Virgo. I think because I mean there will be
Okay.
observing runs. And actually, there are many avenues, for example, to detect primordial black holes. For example, one avenue is looking for light black holes. So this is within reach of LIGO and Virgo. So if you were to detect a black hole that is lighter than a solar mass, I mean, that would be hard to explain with astrophysics. So that could be a possible avenue towards detecting primordial black holes. Then you will start to have events, merger events at larger and larger redshift, for example. And so this can distinguish between primordial and astrophysical black holes, because you expect a different scaling with redshift for the merger rate. So yes, with LIGO and Virgo, with the future updates, you can do more and more. But I mean, for these over densities, I really don't see any other. These over densities around massive black holes, those are not within the reach of LIGO and Virgo. And Euclid, I don't know how it can be used in this context.
In your plot, when you show the frequency and so on, I think Euclid is at higher, but I might be, yeah, there. So I didn't see it, and I don't know where is the spanning from.
Actually, with Euclid, you can, you can do a lot of things. You can map the larger scale structure basically, and you can test, alternative gravity theories. But in this particular context of, determining whether there is an this very peculiar gravitational wave observations, right? So no, I don't think. I think you can do a lot with LIGO and Virgo. So I think you can do a lot with studying. You can study the merger rate of black holes at very high at increasingly high redshift. You can study the mass function of the black holes with LIGO and Virgo. So while waiting for LISA and ELISA, I think LIGO and Virgo are very promising. Euclid, I have to think about complementarity, but this peculiar system, I don't see it in any immediate way.
It was just a curiosity. Thanks. So there is a question from Lawrence.
Yeah.
Yes. Could you say, maybe I didn't catch this, how much mass is in the spike compared with the mass of the black hole? And also, does the dynamical friction change the shape of the, if you had a spherically symmetric spike, does it become aspherical? And do the orbits get biased in the dark matter as well? What sort of distribution function does the dark matter have? And how does that change from the dynamical friction?
Okay, so it would, okay, so the profile would be altered. Yeah, so you would partially deplete basically the spike, right? So in particular in the outer part, but still there will, I think, and then you will also change the symmetry of the problem, because you have this inspiral. So instead of having a spherical symmetry, this depletion would correspond to the orbit of the compact object. So yes, you will change a little bit the symmetry of the problem. The total mass is smaller than the mass of the central black hole. It could be comparable if you consider the overdensities that are expected around primordial black holes of like 30 or 40 solar masses. So in that case, the mass of the halo could be comparable with the mass of the central object. In this case, it would be lower, way lower. And then, yes, you can expect an alteration of the profile, but maybe I missed the last part of the question. So what were you referring to in particular?
No, I think that, and maybe just one extra, is the extent of the spike limited by the tidal fields of whatever the intermediate black hole is in? I mean, there's the Hill radius, that we talk about in planetary systems, that sort of thing. So is there a tidal truncation of the spike from its environment?
Yeah, that's a good question. Actually, the spike should form in the very early universe. So the whole thing is the competition between, the competition between the gravitational pull and the expansion. For example, for primordial black holes, the expansion of the universe or the Hubble flow. So basically, yeah, there is a truncation. You can define a sort of sphere of influence of the black hole, right? When the gravitational pull overcomes the expansion of the universe. this, for example, in the case of primordial black holes. In the case of intermediate mass black holes, there is not a well-defined truncation, I would say. So it really depends on the formation mechanism of the black hole. So for primordial black holes, they're really formed very, very, very early on in the history of the universe. The truncation is set by the competition between gravitational pull and expansion of the universe. For intermediate mass black holes that are still formed in the very universe, but a bit later on, and so they are basically, you are growing your spike adiabatically from an overdensity is already present. In this case, I don't expect a truncation, but I should check. I mean, I haven't looked into that because we are considering systems in which we are already well deep into the spike. So I'm not super sure, but I wouldn't. It depends on which kind of black hole, and it depends on the formation mechanism, I think. That can change. In the case of primordial black holes, I would expect some truncation due to the competition of these two effects.
Okay, thank you.
Thanks.
Are there any other questions, comments, curiosity that you would like to ask Daniele? No.
Yeah.
Okay. So if no other question, I would like to thank you again. There are some reactions that I can use. Thank you very much, Daniele.
Thanks.
Let's be social while being virtual.
Yeah, thank you.
Thank you very much. And I would like to remind all the others, there is no seminar next week, but there will be a special journal club this Thursday. And you should all have received an email from Cindy with the link to the Zoom and everything else. So again, thank you very much, Daniele, and see you soon and talk to everybody else later. Thank you. Bye.
Goodbye. Thanks.
Ciao, ciao. Grazie.
Ciao.